Stream. Welcome back. I've got something to tell you. I've got to own up. I didn't stream yesterday. I know. 27 days straight. Coming in on the final stretch, and I have no excuses. Though I will note that I spent my time I normally would stream doing Bayesian statistics. Specifically, I had homework where I had to code up some Monte Carlo simulations, and technically I was doing similar things I was doing here on stream, though some of it involved doing some more heavy background mathematics, so outlining some of the derivations for the likelihoods and priors, and then building the actual algorithms that would go through and implement these sampling strategies that we allow the software that we use here in the video series to do. When I get to watch the pretty bar say initialize, and yeah, so last night I spent a bunch of time doing that, and unfortunately that made it so that I wasn't able to stream. I finished like 11 something. I wouldn't even have been able to go for like an hour, and I wanted to ensure I got some sleep. So we missed a day, and owning up to that. Though I am still going to, rest assured, I'm still going to try to get to the remainder of this book. I might have to stream a day away, so that will be interesting, where I won't be able to have my microphone here. But I think that we'll manage. The sound quality might be a little off that day, but it's more, like said before, it's about engaging with the content. And I think that given the spirit of that, engaging with the content, what I did yesterday counts here. But I did not get to log on and do yesterday, so here we are today. Bayesian Cognitive Modeling, the series where I go through all the exercises in the practical guide by Wagenmaker and Michael Lee in order to learn how to conduct Bayesian inference and some of the workflow or practices for thinking about questions in the cognitive sciences that would involve using Bayesian analytic techniques, or that one could use them. These types of techniques to answer the questions of interest here. Last time we opened the chapter doing the heuristic decision-making stuff. We're going to continue doing that today. So we'll just get right into it. Oh boy. Oh. So last time we were looking at the taking the best bet model, which was a model of choice that involved this concept known as Q validity, and it's this criterion where over a set of stimuli, if something had high Q validity, then it's likely that you took that as your decision amongst the tasks, or amongst the questions like which of the two professors had high salaries. Right. Outline some of the assumptions of the test. All stimuli are represented in terms of presence or absence of some common set of cues, and then these cues have Q validity, and if the Q validity is high, it's likely that you pick that because it's the best bet. And we spoke about the task that people go about capturing the effect of taking the best bet. So they had, in this particular experiment, they had 20 subjects answer 30 questions. And then on each trial, they did these assessments between the two stimuli where they had to make a choice they searched between information, and they had the option to search for information when making an assessment between the two options, and they could decide when they didn't want to search and make a decision. And so this provides us a lot of information about whether people are following this sort of take the best bet model. And here's the graphical model then, where we have the choice A, B for a given question. And then each subject for question, we have the what they chose, so A or B. And then we have this consistency parameter. Well, what I was thinking about it as a consistency parameter, but it's supposed to represent the compatibility between the predicted choice for the take the best bet model and the choice that the subject makes. So there's this sort of continuity. And if we have a gamma here that's high, then we'd expect that the taking the best model, that the person's choices were very much in line with what we'd expect from the taking the best bet model. Right. Well, based on what choice they picked, taking the best model would predict some probability of them choosing that one. And if it's B, then they had some probability of choosing the other one. So the amount of the consistency with taking the best bet model someone has is the parameter that drives the predicted choice that they make for a given question. And as we saw, taking the best bet model is pretty accurate. Accuracy being here, we saw it did a great job at predicting what choices subjects made. And now it's stopping. We're going to address an additional assumption that this sort of paradigm of choice makes about the decision maker. That is that when looking at the Q validity, or when applying the taking the best bet heuristic to discriminating between Qs for a decision, one Q could be enough. If the Q validity was high for that Q, then I'd stop. Why search anymore, right? Though that sort of automatic stop, some people might want to explore options. It's possible that there are other models for why people might stop searching for information, and it'd be important to use the taking the best bet heuristic and compare it to those models. Excuse me. And we can do so here in the example, or we will do so in this example. And I've got some old Easter candy, mini eggs. And so we're going to examine or compare the taking the best bet model to a model called the weighted additive model, the WAD. Okay. Which sums the evidence for both decision alternatives over all possible Qs and chooses the one with the greatest evidence. So rather than just picking the option that had the highest criterion value for with respect to the magnitude of Q validity, the WAD is taking a odds ratio or a proportion, and from this proportion it is able to discriminate or give a weighted account of the evidence across multiple Qs. So it can provide the total proportion of or weight of evidence across multiple Q validities, and then based on that value of that average or that quantity, the proportion that they calculate, based on those calculations, then whichever one is the largest one is the one they choose, right? And we can, at its core, that makes sense too. So that's the interesting about these models, where both make a fairly reasonable sense and could be provide alternative explanations for what's happening during the decision-making process here. So why don't we compare them to one another and see if subjects are using one strategy or the other more often, or is it the case that it's more question specific, where for some sorts of questions people are using one sort of heuristic above and beyond the other. And we can embed that into our graphical model, actually, and we can just go ahead and test for whether subjects are using the taking the best bet or the weighted additive model. And we can do so by using what we did in chapter 6, the mixtures. And the mixtures have come up several times over this book. We actually just used the mixtures in I believe it was the multinomial processing trees example as well, right? Yeah, when we were looking at, no. It was the generalized context models for categorization. We were categorizing types of ways to approach discriminating between or categorizing stimuli, and various ways that one could place weight, attentive selectiveness on the dimensions of the stimuli. So we could estimate some latent group. Where here we're going to estimate a latent mixture, which is going to be a indicator variable for whether whether an individual whether a given individual scores corresponded more so with the take the best bet model or the weighted additive model, right? Cool. So we're gonna take a look. It's in stop text, and I have some intuitions here that tell me I'm gonna go into the doc here, and my JAGS model is gonna be gone, but we'll see. Yeah, no JAGS models. Stop J. There's a MATLAB script in here. But the data is not even in here. Is I missing the data? Yeah, I don't even see the data in here. Oh, years and years, and no one has mentioned that the book was missing these files. It's concerning. But they couldn't be gone forever because looks like we have some of the data here. Oh no, looks like we got a nice Stan model. We'll set this as a working directory. We'll open Stan and we'll grab some of the standard recommended options. And then we can just oh no. Let's see what we got here. We got several diagnostic errors in the parsers, though none of which seem to be impeding Stan from doing its thing. There she goes. And mostly good. Okay. So we're getting that accuracy chart again, and then it looks like I assume that this is going to be our Z indicators. And keep in mind Z is 1, then it was TBB. So these are take the best bet subjects. And these are then weighted additive subjects. Like subject 2, for example. Something interesting we can do here. Look at subject 2 and then look at here, subject 2. Oh, but this isn't in subject order, right? Those are for the questions. Subject 2 here. Well, subject 2 is pretty responsive, though. Maybe I'm reading it wrong. I guess we'll find out. Alright, let's read the WinBugs code, just to massage in some more WinBugs code, and then we'll turn to the interpretation, and we'll move to also read the Stan's code too. I might have to grab my Stan textbook. Alright, so stop text implements the graphical model. So each subject for question, then y for given subjects for question is distributed Bernoulli, where we have this decision where T for a given subject for a given question with the ZI indicator for that subject. So this is going to give us our gamma. But where is it itself calculated, right? So 1 minus gamma. This is the 3 decision rules. Guess, gamma, so consistent with option, or 1 minus gamma. And gamma here, this consistency varies depending on which of the decision heuristics we're using. this is for prediction. To do the predictor checks, this. So here's the take the best bet model, coded up. Each subject for Q, number of questions. Look at the Q contribution, and then give me the maximum, whichever one's the largest. So if a Q favors a stimulus for a given question, that's the Q that gets picked. It just wants me to, or the point of this is to identify which Q is picked. For one is take the best bet. So we get this T that's going to tell us which decision rule we use. Or it's going to tell us, give us the information, the prediction information for that given decision heuristic. And then, let's see, Q search. Order. Look at the order of the value. So 1 to the number of Q's, give me the Q as the largest, or give me the order of the Q's. This is for each of the Q's, right? What is V? So give me the search order that follows the V's, the validities. But where do I get the validities? That's data we bring in. It's because I haven't had the opportunity to look at it. Let's load it. What be the data? All right, so here are the Q validities. We load in these values, right? Because these are knowns for each of the questions. Subjects, 30 questions each. This is the dichotomies, binary responses to each of the questions for each of the subjects. Number of Qs, 9 Qs. And so after you build out the take the best bet and the calculation for the weighted additive, I see. So it ends up being here and here. So this T for the, it's the choice that would be given for each of the two models, right? But based on which one it picks is indicated. So each subject we're estimating the WAD and the taking the best bet model for, but Z is going to tell us which one gets used or is likely to be the one being used by a subject. So this sets up the latent indicator, and then we just have a gamma prior for our consistency with whichever the model and the person's predictions, and phi is set up as the probability of being one of the two options. So uninformative prior. So with respect to the summary from the last time, we see a 68% increase in terms of correspondence with human decisions. So our model can now also predicts a substantial additional amount of people's actual choices. That makes sense because we've provided a larger net in terms of possible approaches that a subject could take. One could then imagine expanding this further, where we have a whole vector or series of other models or heuristics that people might be using, like a scheme of a series of heuristics that we could then map on the probabilities of people using one scheme or another for a given set of choices. So we see subjects we get a lot better performance in terms of predictions. Here, for example. Because those are the subjects who we now believe or would predict, given the z variable that we inferred, a latent indicator that we inferred, that they were using the weighted additive approach rather than the taking the best bet. And then we can look at the latent mixture results, where values low here are representative of like what we said, be using the taking the best bet model. That would make sense. Wouldn't one be able to predict these values then? Because like 2, 4, 20, for example. Yeah, this must be the wrong. Yeah, I think this is wrong because these subjects are all in the WAD group. So plot and interpret the posterior distributions for phi. Approximate and interpret Bayes factor. I can do that. At least half the subjects are highly certainly belong to the WAD group. Okay, so let's take a look at the stand code, and then we'll walk through and answer the question it wanted us to address here. And we'll do so using some of packages here, like Bayes. base plot. And I've never used base factor before either. Just looking at some potential packages that might be cool to try out to do the base factor question it asked. But I think I just stick it or kick it old school and okay. Let me get my textbook. Data int is continuous. Okay, so we have a discrete variable, number of subjects. And we have a discrete variable for the number of questions, discrete variable for the number of conditions. Is NC number of conditions or number of Qs? Okay, then we have another variable y, which is size, number of subjects by number of questions. So 20 subjects, 30 questions. Then we have another variable m, which is size 83 by Qs. What's in M? M, the predicted choices for each of the 9 Qs. It just represents for one. Represents the Q that gets used. When do we even use M? It seems like some matrix to help us identify whether or not a Q should be considered for a given question, but for a given, not question. And I want to think option too, but 9 Qs, 83 options doesn't make sense. Even with 30 trials, 83 options would, I mean, maybe there's more options than there are trials, and we randomly choose. This is like the pool. I like that. And then we have P, which is for each of the questions is going to have some probability P for each of the two decision rows, right? And then we'll have two vectors, which will V and X. V and X be something about the Qs. X. More things about the Qs. There's some more. They're both size 9, so it has to be something about Q weightings. So we're going to make another variable bounded from 1 to the number of Qs. We'll call it S. S here is going to be what contains the Q validity for a given trial, right? We don't directly look at S here in this model. Up top we did. But you can see this is in transformed data because to these parameters are initialized by using information from the data. So we're going to take in these values from the data in this list. So all of these are one of the elements in this list. And Stan expects a corresponding element in the data list for each of them. And then we use that to create parameters that are specific to some of the internal dynamics within this model, or the assumptions in this model. So we can determine, for example, the size of the S, which contains all the criterion, only by knowing the number of criteria Qs we have. Q validity, right? So the number of Qs to have Q validity. And then continue with this array here by number of subjects, number of questions by 2. So T giving us, T can be from 0 to 3 and contains enough for each of the 2 decision rules or heuristics for each subject, for each question. Three, why? No idea. Because, I mean, it's only ever going to be 1, 2. I guess this is just to prevent, or, the possible spillage. I don't know where the spillage would come from, but it's a safe bet that values beyond that range wouldn't make sense, though values in that range, we expect all values to be within that range. So now we can determine S. Change as I go along. Which sorts ascending order the Q validities. And now let's set up taking the best bet model. Nested loop. Some vector, we'll call tep1. Some continuous variable, call temp2, and then some discrete variable, we'll call it temp3. And we're going to use temp3 to give Q contributions to each of the decisions. Right, so this is like a true or false thing, where for each of these, we're going to impute them with these values from that's cap. Use the V's in ascending order. So temp1 is just going to be the Q's of interest, which are identified using the Q validities and the M matrix, the pool of options, I think. So then take the sum of temp1. So give me the sum of all the Q sum for the q, and then temp3 is -1 times in step. I haven't seen in step before. So logical function. So these are logical functions that are mostly, so just reading the documentation, the reference documentation for Stan. These are sort of these are conditional functions which work like step in JAGs, where if you meet some condition equal to 1, if not equal to, or if you meet some condition equal to 0, if not equal to 1, right? So -1 times if negative temp2 some condition. If the sum of negative temp2 is less than 0, my thing is negative temp2 will always be less than 0. Or I guess it's not negative temp2. If the inverse of temp2 is 0, multiply it by -1, I see if the inverse of temp2 is less than 0, multiply it by -1, this is going to give us a positive value. And then we can add it to if temp2 is temp2 is equal to 1 or 0. If temp2 is large, that's going to be equal to 1 here. And then the inverse of the large value would be negative, so it would be equal to 0. I see, so this ensures that we get 1 or 0, and then we add 2 to it. So if we add 2 to 0, we'll get 2. If we add 2 to 1, we'll get 3. But it's also supposed to be 1 and 2, so I might be doing something wrong here. Either way, this is fancy for, it's going to give us a 1 or a 2 based on what the sum of the Q favors, evidence-wise. And then the weighted additive decision model here. Set up this vectors, temp vectors again. Initialize the temp4. Find the Q that favors this initialization. So we characterize the heuristic, assess the Q that corresponds to what the heuristic would predict, place that as the prediction in T. We initialize our parameters, here gamma phi, and then we initialize some other parameters. Oh, I noticed I wasn't doing something while I was going along. Hold on. Let me put in the equal signs. So I don't get, it doesn't scream at me. And what was wrong over here? So we got those. The first thing it said, deprecated Bernoulli log is the next thing. We'll get there, looks like. Okay. Initialize the parameters. Vector LP parts. LP parts is what? LP. It's a log probability. Yes. LP parts unfortunately sounds like a business, so I'm not finding anything on Google. It's funny though. Log probability though. I'm gonna assess. So vector size 2, log probability, number of subjects. Vector size 2, log probability, fill it log probability for each subject, for the number of subjects. Set up the decision weights. We initialize the decision parameter here. Vector size 3. Call it deck. And then each of the elements in the vector are characterized by these. When I say characterized by these, I mean characterized by equal signs. So now we're setting up the mixture. Please use I don't know what you mean. I'm gonna find out though. So Bernoulli log probability mass function is, rather than just Bernoulli log, just this should work. I think I'm supposed to use probability mass function here. Cool. What about this? A composed function, you say, is the natural logarithm of 1 minus x. Natural log 1 minus x of phi gives us this part, then log of phi plus the sum of the temp. So get the probability mass for the choice at this decision rule, and then use this temp. Get the sum of all the temps from each of the questions plus phi, that baseline probability, and that gives us the probability from being from the take the best bet for this subject, and the probability of being the WAD for the subject. So each subject's going to get each of these. This is just summing it. 1 minus here, I assume. It has to do with the direction of the indicators, the possibility for negatives, maybe. Because this is going to be from 0 to 1, but this is going to be up to 2, so we minus 1. Or at least that's what I'm guessing now, based on what we saw before. We're looking at 1s and 2s rather than 0s and 1s. Excuse me. Now we set up the priors. Anything else is needed broken. Bernoulli logs fixed. Increment log prob is done as well. Oh, well, first we miss these. And now phi. So let me see how to write this out appropriately. Now we write target plus equals prediction for Z. We generate Z, right? So Z is derived from all that what we did above, using the log probability parts. We run it through a softmax. What is a softmax? You ask. I don't know. It's a special matrix function. It solves some sort of simplex formula. Calculated on the log scale. It's just calculating some matrix. Then we get Z using prob. Looks good. Let's see if it runs now. Oh, parser error. A vertical bar buffer. Let's see. There we go. And we got no errors this time. Or no. But see, Stan gave some excellent advice about what was broken. Thank you. But we didn't get any notes. Diagnostic notes, which is cool. So our syntax was proper. Or we wouldn't gotten to the stage. It looks like, oh, and it's on the roll. It looks like it ran even maybe a little faster. I mean, let's see, 1.25, total 1.5 seconds. Up here, 1.6 seconds. Yeah, we cooked. We saved 0.1 second by updating that syntax or just variability. Great, so now we can look at the posterior distributions. So let's take a look at the posterior distribution for phi, which is the baseline probability for choosing between being from one of the two options. First, let's print out the samples. And let's take a look at phi. Gammas. Alright. I'll just do one better. I'll get a little fancy here. Give me samples. Uh-oh, I need to open up the tidyverse. Tidyverse unlocked. Samples. Give me 500 Posterior predictive checks. I don't want to do that. I just want the area. Let's see. Posterior. Maybe this will work. Take the samples and then give me phi. I want phi. And heck, I'll even look at gamma. Oh, fat phi. Let's just take a look at phi. Here's phi. 80% credible interval. So it's likely baseline. It's more likely to take the best bet model. Right, and that makes sense because we had more people in our sample that were the take the best bet model. Right. So given the sheer volume of folks, it's more likely, rather than being 50-50, that we're just slightly more likely to indicate that Z be for, make sure, the take the best bet model. But let's test it. Let's collect the posterior samples. What is it? Oh, that's kind of cute. Except, not really. Let's collect posterior samples. Phi. Posteriors extract samples for phi. What does that say? Did it extract though? I'm not missing something, am I? This is how you get things out of stand models. using extractor. I think I was just getting confused about which one to use because I loaded the Tidyverse. There we go. We can check that by doing. This should look just like the one we saw. Yep. 50. Just like this one. But less pretty. Cool. Right, we've extracted the samples. Now we'll run that statistical test. Log spline. Fit posterior. Posterior. Now look at the. This is the credible intervals, right? X1. Yep. Now we look at 0. We use the density of the posterior. So this gives us the PDF for phi at 0. And now see our prior in this case for phi is uniform. So we need the height of order restricted prior phi. If I'm not mistaken, it's a boatload of evidence in favor of the posterior not being equal to 0. But is that what I'm supposed to be testing? Null hypothesis is phi equal to 0. Yeah, phi is not equal to 0. Keep in mind. Phi 0 and 1. It's the probability of being part of one indicator or another. So is the probability, so there's evidence in favor of the probability being equal to the alternative rather than null. So there's substantial evidence in favor that the phi is not equal to 0. So what about 50 though? That seems like a much more interesting test. Like 0.5 and 0.5. This time, evidence in favor of the null hypothesis. Slight. So it's possible that we're at a 50% chance. It's evidence in favor that we're at 50-50 in terms of so there's no clear indication of bias represented in our sample of people who are in either using the weighted additive model or people who are using the take the best bet model. It's possible that it's still around 50% that Z would have put them in one or the other. So Z wasn't biased to put people in the take the best bet model, even though we do see this slight shift in the distribution towards higher probabilities, it looks like. I mean, if we looked at the mean, right? Yeah, looks unbiased. That's pretty cool. I wonder if we do this. Does this just give us phi? Nope. Okay. So we answered our question. We did we did hypothesis testing. Cool. I wonder if this code will work for me. I'm gonna give it a go. I only need to make some slight changes, it looks like. Get the phi, the posterior. Okay. This is gonna be phi. Nice. Here's a test at 0. And so not even close. In the light of the evidence, there's no chance that phi is equal to 0. But if we wanted to look at 5. Yeah. Sort of. Not really what I'm looking for. That's better. Should be better. This is the hypothesis we just tested. Ta-da! Evidence in favor of the null hypothesis. More density. Is that what this is saying? Okay, so we just did some Bayesian hypothesis testing demonstrating that phi was significantly larger than 0, though it's not clear if phi was larger than 50%, which is good, given that this model is supposed to, phi is supposed to represent the weighting of z towards one decision rule or another, and it's pretty half and half, which is good, I think. So that's it for today then. Thanks for sticking around. Hopefully we'll get to using we'll get to talking about stopping or searching, which is looks like another heuristic that we're going to incorporate into a decision model, which is cool. Or another characteristic in the decision-making process that we're going to be able to incorporate here. And I look forward to exploring that more tomorrow. Yep.